All right, everybody. Let's see. Is it streaming? Yes, it's streaming now. It's time to do this. Okay. Right. This is lesson 2.8 on functions. Once you watch this video, you'll be able to define what a function is in terms of inputs and outputs, what makes a function. And then we have different ways of describing functions. So for an arrow diagram, I want you to be able to recognize when it isn't a function, how to evaluate it at a given point. I want you to be able to define the domain and the range of the arrow diagram. For a table function, recognize when it's not a function. Evaluate a function at a point. Use the table to define the domain and define the range of the table. For a graph, for a function just driven as a graph, I want you to tell me when it's not a function. What would make it a function or not a function? I want you to be able to evaluate it at a point. I want you to be able to define the domain, define the range. And for algebraic expressions, I don't care about recognizing not a function. I want you to, though, to be able to evaluate it at a given point and be able to talk about the domain and the range. After that, I want you to be able to evaluate a piecewise algebraic expression. Okay. So, this particular section of the chapter, this whole chapter actually, is really theoretical. In math, in the culture of mathematics, it's really common to have it set up. The explanations in your book, the explanations in your courses, it's really common to have it set up so that you spend the first little while talking about definitions and ideas. And then you spend more time after that putting all these ideas and definitions together. And we find ourselves doing that right now. This chapter, for the most part, is mostly theoretical. There's not many computations to do. There's not many calculations to do. Mostly it's just we talk about ideas, we talk about what the ideas mean and their consequences, and we define terms, and we talk about what the terms mean specifically. So it's important to be able to know what we're talking about, especially in this case, because the later chapters rely heavily on some of the ideas that we use in this, and not just here, in future chapters like or in future math classes rely heavily on the material that we're covering today. So this is an introduction to a concept called functions, and functions are ubiquitous in mathematics. That means you see them a lot. They show up in lots of different types of math, including calculus. So we're going to talk about it. It is fairly conceptual. We're talking about very broad concepts that get used specifically, but given that we've already seen some functions, so polynomials and rationals, expressions are both types of functions, given that we've already talked about some functions, it's going to give us a good grounding, a good basis to be able to talk about things in the future. All right, so let's begin. Okay. So I'm not going to mince the truth. You've already seen a function. Polynomials are a type of function. Okay. In fact, you know how we were naming polynomials? The reason we usually start their names with the letter F is because of functions. This is a function of x. Okay, so how do we use this? Just like how did we use polynomials? They were expressions, we gave them names, and they had a purpose, right? Somebody would give you an input, and you would take that input and use the expression to calculate an output. In this case, you'd plug in the numbers. 4 plus 3, 7. So 7 is the output corresponding to the number 2. So this is true for polynomials, and it's also generally true for functions. We can think of functions as machines. You know, it's a machine And on the front of the machine, there's a big number pad. Boop, 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 boop. And you go up to the function and you input a number. And then the function thinks about it, the machine thinks about it, and then prints out another number. So the function in this case is the machine that takes the input and turns it in the output. In this case, in the case of polynomials, this expression was a function. You plug in an input and you use it to calculate the output. So what, generally speaking, like what makes a function a function? For example, like if let me look at a specific case here. Here you go. X plus 2, x plus 3, and x squared plus 5x plus 6. If you evaluate this one, you get that one if you expand it, and if you factor the polynomial, you get the other expression. So they're in some way equivalent. Are they the same function? I mean, they look different. Well, for this particular pair, any input I choose, so if you choose x is equal to 3, you get on this side it's 3 plus 2 times 3 plus 3, so that's 5 times 6, so that's 30. For any number you choose, all right, so 9 plus 15 plus 6, so that's 30. For any input I choose, both of these expressions always give out exactly the same value. And so these two expressions are the same function. Even though they look differently, they're actually the same function. Because the function isn't how it looks on the page. That's not the function. The function's a relationship between numbers. Relationship. Wait, hold on. It's a specific relationship. Input numbers and output numbers. Okay? So if you put in an input number and it gives out a different output than 30, then you know that it's a different function than this one. Okay? So there's some aspect to this that's general, which is to say that the function is the specific relationship. It's not any particular equation. It's the relationships between input numbers and output numbers. Okay? So there's a variety of different ways to talk about functions, to display a particular function. Writing things as algebraic expressions is actually one of the least obvious ways of talking about a function. It's hard to tell what people are talking about when they're writing a function out algebraically. So here's our first way of talking about functions. This is called an arrow diagram. And what you have in an arrow diagram is you have a set of numbers on one side and a set of numbers on the other side. And then there's a set of arrows, like that. And the arrows go from one set of numbers to the other set of numbers. It doesn't really matter which one's on the left or on the right, but what matters here is that it's always from one set to another set. Okay? And so you would call this the input, maybe. You call that the input, and this one the output. And the arrows there represent the relationships between the two sets of numbers. Okay? And so we can use the arrow diagrams to look up the outputs for various inputs. So let's look at here. When x is equal to 1, the f function gives me back, and then so you look at 1, and you follow the arrow down, and it's 2. So that output is 2. When f is equal to 3, the output is 5. And when f is equal to 4, the output is 4. There's nothing saying that for a specific function, your arrows have to like look pretty or anything. They can cross each other and they can do all sorts of stuff. The important detail though is that you just follow the arrows to figure out what the outputs are. Why don't you try the G ones before we go on? All right. Well, what'd you get? So when G is equal to 2, you follow the arrow down and you get 3. When G is equal to 3, you follow the arrow across and you get 3. And when G is equal to 1, you get 1. Okay. So let's review what we've talked about functions and in this specific context, and then I'll teach you some new things. So first thing is that number 1, f and g are different functions. How can you tell they're different functions? It's because a function is a relationship between numbers. It's essentially these arrow diagrams, right? And so they're different relationships. So, you know, the input 1 on the f function gives you 2. The input 1 on the g function gives you 1. The arrows are different. Not just that they look different, they're pointing to different places. They start out in the same place on two different, and they end up in different places. Second, I want you to note something here. Both of these inputs, 2 and 3, go to the same output. And that's okay. That's fine. It's okay to have two different inputs point to the same output. That's okay. You can have a function, heck, you know, polynomials do that all the time. So now for something new, the domain. Domain is a word that's generally used to mean where it lives. So like the domain of the lion is the savannah. Or it's talking about the region a king rules over. So the domain of Queen Elizabeth is all of England and other places. Okay. So in this context, the domain is the set of all input numbers. Okay. And this might be different for different things. What do I mean by the set of all input numbers? Well, in one sense, I mean all the numbers over here or all the numbers over here. But in another sense, I mean all of the numbers where if I plug the number in, I get a number out. Right? So 5 here is in the domain. So for instance, 6. 6 is listed inside of this input pickle, but it doesn't have an arrow attached to it. It doesn't go anywhere. So if you plug 6 into the function, the answer does not exist. 6 is outside the domain. What about that one? Is 7 inside the domain? It's not even listed inside of this input pickle. So as a result, we say that 7 does not exist. So by input numbers, the set of input numbers, we mean all of the numbers that kind of have an arrow attached to them. And so we can list these, especially in these cases, in these little arrow pickle diagrams. It's fun to list the domains. So the domain of f is number 1, 2, 3, 4, 5. The domain of g is 1, 2, 3, 4, 5. Note that 6 isn't in the domain because it doesn't have an arrow attached to it. Okay. Now, here's another word. This is called the range. Just like the domain talks about all of the numbers in this that have arrows attached to them, the range talks about all the numbers in this set with arrows attached to them. So the domain of f in this case is, the range of f is 1, 2, 3, 4, 5, but the domain of g is 1, 3, 5. What about 2 and 4? 2 and 4 don't have arrows attached to them, so it's not in the range. I want you to make a note here. When we're talking about the domain and range, what we aren't talking about necessarily is the numbers inside. Oops. What we're not talking about is the numbers inside these pickles, okay? Because the function, the domain is in terms of the function, right? And the function isn't the pickles. The function is the purple arrows. So it's all the numbers that they're attached to. These ones are all the numbers the arrows are attached to on the left-hand side, and these ones are all the numbers they're attached to on the right-hand side. Does that make sense? Okay. So that's functions as arrow diagrams, but it's important at this point in the game to talk about what's not a function. So here we have a pickle diagram, an arrow diagram that isn't a function. Why do you think this one is not a function? It's because the arrows are different directions. To draw a function, functions are always, I mean, this is a relationship between numbers inside the pickle diagrams. It's definitely true, but the arrows always have to go one direction. They always have to go in this direction, or they all have to go in the other direction. They can't go both. This one is not a function in a much more interesting way. All of the arrows are pointed in one direction, so that's correct. The thing that doesn't make this a function has to do with ambiguity. The idea here is the way a function machine works, for any number you put in, you only get one number out. The answer can't be ambiguous. The answer might be no answer. So in the last one, you saw that, what was it? G of the number 6 gave no answer. That's entirely possible. But what isn't possible in terms of functions is that you get 2 answers out. What do I mean by this? Well, okay, so we can evaluate this function. 3, oh geez, let me rewrite that. 3 is equal to 3. F4 is equal to, oh geez, 3. Both of these, oh, come on, just once in my life, I want to write the number 3. There you go. Okay, so both of these inputs correspond to the same output. And I said that that was totally okay, and it is. That's not ambiguous, right? For this one, the answer is this one. For this one, the answer is this one. It's the same, but who cares? It's unambiguous. That's not true for 1. For this input 1, which destination do I go to? There's 2 arrows. It's like when you're at the airport and you get told to go 2 different gates. Which one do you go to? Because it's not clear which one this arrives at, because there's more than one arrow coming from that point, this is not a function. The output is ambiguous. So to review, it's entirely okay if 2 inputs correspond to the same output. If 2 things go to the same place, that's okay. What isn't okay is if one input can go to two outputs. That's no. Okay? So that's a basic attribute of functions. F of x can only have one max output for each input. This is the cardinal rule of functions. We're going to see this in a variety of ways over the course of this lesson. Okay, so pickle diagrams are fun, but it's easy to, or rather, it's straightforward to look stuff up on a pickle diagram. You just follow the arrow, right? But it's not very nice looking, and it can get very, very, very busy. So a more efficient way of talking about functions is to use a lookup table. Here we go. It's just a table of numbers. One way to think about it is imagine like the phone book. That's an example of a lookup table. And the idea is it's a table of elements where you have essentially a name and then a phone number. Does that make sense? So let's try evaluating some functions using a table. When f is equal to 2, that's this function. When it's equal to 2, you look at that input and then you look at right across from it, right where it's easy to see, 3. When f is equal to 4, that one, the output is 4. When g is equal to 1, that's this table, the output is 1. Does that make sense to you? It's just a lookup table. You just look up the number. You just look up the number inside the parentheses, and then on that row you get the output number. So lookup tables are great for describing functions. So let's go through the same points that we went through in the pickle diagrams. I should call them arrow diagrams and not pickle diagrams, but I am unrepentant. First, these two diagrams are different. How do we justify the claim that they're different? Like, you know, I say they're different. What makes them different? Just because they're written side by side? Just because they have different names? One might be going by an alias. How do you know they're different? Well, they're different because for an input, you get a different output. That one, input 1, you get 2. This one, input 1, you get 1. They're different. The outputs don't match. It's pretty easy to tell if a table's the same or different. So the table's different, so it's a different function. Okay. Next thing I want to note, similarly, we saw this on the previous example. All of these inputs have the same output, and that's okay. For different inputs to have the same output, that's fine. It's still a function if that's true. 3. What's the domain? In this case, just like in the previous case, the domain are all of the numbers that you can look up. But not just. They are all of the numbers that you can look up that have outputs. So 6 is in this table, but it has no output. Okay? It's a lot easier to write out the domain of these functions than it is in a pickle diagram. So for f of x, the domain is 1, 2, 3, 4, 5. That are these numbers. For g, the domain is 1, 2, 3, 4, 5. And again, there's something called a range. Get out of here, you. The range is a little bit less apparent in a table than it is in an arrow diagram. The range are all of the numbers that you can output to. Okay? It's easy to list in a table. It's tricky to list without repetition, but you can repeat it. It's fine. 2, 3, 5, 4, 1. And maybe after you might want to sort it, but you don't really have to. 1, 2, 3, 4, 5. Okay? So you don't have to sort it, it's fine. So that's the range, all of the numbers that you can output. What about g of x? 1, 3, and 5. 3 gets repeated 3 times, but that doesn't mean anything. Does that make sense? So the concept of domain and range in a table is exactly the same as in one of those arrow diagrams. Essentially, we're just, what are the numbers you can plug in? What are the numbers you can get out? That said, not every table is a function. How about this? Here are 2 tables, f and g. One of them is a function, one of them isn't a function. Let's find the function first. Well, what's strange about these? I'll highlight what's strange. This one's strange. 1 is repeated. 1's repeated in this one too. Is it bad for something to be repeated? Well, we mentioned before that the cardinal issue is one of ambiguity. If I enter f is equal to 1, or g is equal to 1 for the repeated one, what do I get out? For g, the answer for f, the answer is either 2 or 4. For g, the answer is either 2 or 2. Well, these two are different numbers, and that means that for the same lookup, you can get a different, for the same number looked up, 1, you can get different answers. And that's bad. That means that f is not a function. What about g? Is g a function? Well, these are the same number. Just because an entry is in the table twice doesn't mean anything. Essentially, as long as the input corresponds to the same output, we're gold. Things don't even have to be in order. These numbers don't even have to be in order. I mean, it helps if they're in order. It helps to interpret. But this means that f is not a function, and g is still a function. So let's find the domain of g and the range of g. Why don't you pause it and try it now? All right. So the domain is all of the inputs. 1, 2, 3, 1 is already there, 5, 6. What about 4? 4 is not in the table. These are all the inputs. If somebody asks for any input other than these, you say, you don't know. It's not in the domain. What about the range? The range are all the numbers that can be output. 2, 3, there's another 3, there's another 2, 5. Okay. So that's how to talk about the input and output of a function written as a table. And before we go too further, let's just emphasize here that there are good and bad aspects of displaying functions in different ways. So, for example, poking up, arrow diagrams, it's easy to tell the domain and range. For tables, it's medium. Tell, domain, and range. It's not so easy. They're not in order. It's harder to tell. It's easy to tell if an arrow diagram is a function. For table, it's kind of tricky to tell. Well, I mean, like, it's medium difficulty. You pretty much have to go through the table to see repeated elements and then see if the same input gives you two different outputs. So, what else is good? You know, tables, they're accurate. There's no ambiguity in what the output is. Same thing for these arrow diagrams. So what's the... and both of these, it's easy to look up. Might be slightly easier in an arrow diagram than a table, but in either, it's easy to look up output. It's just straightforward. You just look at it in the list. Okay, there are weaknesses, though. Problem with an arrow diagram is that it's messy. It can be very confusing. Another problem, they're huge. They're very large. Another issue is that it's like it has limits. So like you can write 1, 2, 3, 4, 5, 6 in one of the arrow diagrams, and that's fine if you only have 6 terms. What about 1.1? What about 1.25? What about 1.03708? Right? I mean, those tables get very the arrow diagrams get very, very big and also very busy. The busyness of the arrow diagram is not in a table. Tables are simple. Simple to look at, simple to interpret. They have bad aspects too, which is that they can be very large, right? So you can put 1.1, 1.02, 1.35. You can have as many lines in your table as you want. You can start a whole spreadsheet full of them. You can have 10 million different lookup things, like the phone book of New York City. That's fine. For the really large ones, it's actually kind of time-consuming to look through them. Arrow diagrams are good. You can also do reverse lookup, which isn't a procedure in terms of functions, but I mean, like, it's something when you talk about phone books. Somebody gives you a phone book and phone number, and you want to look up whose phone number it is. It's fairly straightforward. Arrow diagrams and tables are both pretty good for those. Okay. So they're good and they're bad. Mostly for both these cases, the fact that they're, you know, for any decent function, that they can be both enormous. They can take up an enormous space, kind of counteracts how easy it is to look stuff up with them. So they're fairly straightforward in some cases. I'm not sure if you know, but the sine function and cosine functions on your calculator used to be given in terms of tables. I'm not sure if our university is old enough. One of these days I'll go look. If you go to an older university, you can actually go to their libraries and look up sine books, which are just tables of numbers where there's some angle and then sine of the angle, and you just look it up in a table, and it's bonkers. So tables are actually pretty good ways to display functions. They're compact and you can interpret them fairly easily, so you see them in a lot of places. Arrow diagrams, they don't get used very much at all. They're kind of childish. So, you know, essentially, all of the work in an arrow diagram that you have to draw all these arrows and then interpret all these arrows are just summarized in a table diagram by just putting the numbers right next to each other. So table diagrams are, table functions written as tables are pretty common. So there's another way to talk about functions, and that's as graphs. So functions can be displayed like graphs. Here are two graphs. They're both functions. Before we do anything else though, I want to talk about looking up the value, the output of a function using a graph. The way it goes is there's an x-axis, an input axis, and an output axis, okay? And the functions are relationships between sets of numbers, right? If you give me this input, what's the output? The functions are described as these lines. And here's the way, and so you can look up the output for any input the same way you would in a table. The procedure is slightly different though. So for when x is equal to 1, the input's 1, you go to 1 on the axis. And then you go straight up or down till you meet your function, right there. And then you look at how high off the axis you are. So the output of that is 4. When x equals 2, the output is 4 again. When x is equal to minus 4, that's here, the output is plus 1. When x is equal to 8, the output is plus 8. Graphs aren't usually jaggy like this. A lot of time we're going to be seeing swoopy, wiggly graphs. So do you interpret this any differently? No, you don't. When x is equal to 0, you just look up 0. The output's 4. When x is equal to minus 4, look it up. The output is plus 4 again. I like 4s. When x is equal to plus 2, the output is 1. And when x is equal to minus 2, the output is 3. Does that make sense to you? So you look it up using a procedure instead of, so there's some interpreting that you need to do that's implicit in this graph that isn't that's explicit in the arrow diagram. Implicit and explicit. Explicit means that something is right there explained to you. Implicit means there's something you need to figure out. There's some piece of information you need to know. So in this case, the thing that's implicit is how to interpret one of these graphs. And the procedure is you look it up. X is equal to 2, you look up, blah. Okay? It is really easy to tell whether or not two functions drawn as graphs are the same function or different. If they're different, they're different lines. If they're the same function, the lines overlap. That's very unambiguous. Okay, so let's talk about the domain and range. Now, the domain and range of functions drawn as graphs usually aren't a list of numbers. In the past one, we could list it 1, 2, 3, 4, 7, whatever. There are too many to list here. Usually the interval is pretty big, but I'll tell you what we're looking for. We're looking for all of the values of x that have a graph above or below it. Okay, and usually these graphs go off the page. Yeah, sometimes you'll see little arrows on the end like this, and that means it goes off the page. So if for any value of x there is a graph above or below it, we say that the domain is all real numbers. All values of x. What about the range? How do we talk about the range? To talk about the range, you're going to ask a similar thing. Essentially, whoops, our x-axis ran away. To talk about the range, essentially we're talking about on the vertical axis. So the vertical axis tells us the output. So we say, is there any place on this vertical axis where the function doesn't have a line next to it? So in this case, the line goes up to infinity and down to infinity. It's all real numbers again. In other words, you can't list it. It's got to be talked about in terms of an interval or excluding some set. So here are some that are a little bit more interesting. Domain and range. So first off, the domain. The domain is the function is below and above the whole x-axis here. So the domain's going to be all real numbers. What about the vertical axis? Well, the function's height goes up to here, and then it goes down to infinity. So there aren't any outputs that are above +2. And so the range is, well, I guess its name is g. g of x is always bigger than or equal to 2. Here's another example. So let's domain and range. So again, the x-axis, all of these numbers on the x-axis have a function above it, but there's no function above this part of the x-axis. So the domain is all values of x bigger than or equal to 0. Same thing for the y-axis. The vertical axis. The vertical axis, all these points along the vertical axis, well, hold on. You know what? Looks to me like this gets flat. So let's say that it's 1, 2, 3, 4, 5. The output, h of x, is going to always be between 0 and 5. And now it's time to make a note. There's that line under the inequality. That means includes the endpoint, inclusive. So x can be equal to 0 or any number bigger than 0, but not negative. These, without the line under it, means that it can't be 0, but it can be any number slightly bigger than 0. It can't be 5, but it can be any number slightly smaller than 5. How do you know when to use it and when not to? There's a notation that we use in graphing where there's like a little circle here. You see that circle? That circle means it doesn't include the endpoint. Sometimes, if the circle's filled in, it means it does include the endpoint, and we would go like that. Does this make sense to you? In other words, we interpret graphically. We kind of have to do a little bit of figuring, but you can interpret graphically what the domain and the range are based on what the graph looks like. Here's a fun one. Hey, look, it's got 2 open circles. You know what? I'm going to close one of these circles just for fun. All right, so domain and range. So what values of x is the graph above and below? The graph is below it on this part, and it's above it on this part. So what are those intervals? It's x less than, okay, does it equal the endpoint? Yeah, x equals -2. So it does. So it's less than -2, and x is bigger than +3. Does it include the endpoint here? No, it doesn't. When x is equal to 3, that function's undefined. What about the range? Well, the range is all these values. Oh, it goes down to 1, looks like. And all these values. So the range is that the output is less than or equal to -3 because it includes the endpoint. And also it seems to be bigger than +1. Okay. So that's domain and range off a graph. Interpreting the domain and range off the graph actually isn't a very exact science. It's kind of tricky. If you haven't noticed, you just kind of, you do your best. You might be wrong, you might be inaccurate, but you do your best. All right. Which brings us to our next topic. Is it possible for one of these lines to not be a function? We always bring up whether or not a function, something's a function. So this line can't represent a function. And the reason for that is simple. It has to do with ambiguity. For any one input, I want there to only be one output, right? But when the inputs say this number here, there are 3 points where the line is above or below it. So is the output this number, or is it this number, or is it this number? when x is equal to plus 2 is the output, let's see, that's minus 1.5 or plus 2.5 or plus 3.5. It's not clear what the output is. So in other words, it's possible for a line to not represent a function, just like it's possible to make a an arrow diagram, or it's possible to make a table that isn't a function. Just because it's in the form of a function that we're used to seeing doesn't mean it's a function. To be a function, we have to pass the ambiguity test. For any input, is it possible to have more than one output? If it fails this, it's not a function. Okay, so the last type of function, the last way of expressing a function that we're used to is using equations, algebraic expressions. And you're used to seeing us talk about these. So you might say x plus 2, or you might say 3x squared, or you might say 4x over x squared minus 1. Okay? These are all algebraic expressions, and they're all functions. It's possible to represent an algebraic function as an algebraic function. It's possible to represent a function as an algebraic expression. Remember, a function is a relationship between inputs and outputs. With algebraic expressions, we're telling you what computation to perform in order to count the output for a particular input. So you might say, hey, evaluate f of 3, which is shorthand for replace the x's with the number 3 and then calculate. Or you might say g is equal to minus, how about minus 2? Okay? Minus 2. Or you might say g is equal to plus 2. 3 times minus 2 all squared is equal to 3 times 4, which is equal to 12. 3 times 2 squared is equal to 3 times 4 is equal to 12. Just like with tables, just like with arrow diagrams, and even graphs, different outputs can generate the same, or different inputs can generate the same output. That doesn't mean it's not a function. It's fine. Here you go. H of 2 is equal to 4 times 2 divided by 2 squared minus 1, so that's 8 over 4 minus 1, so that's 8 over 3. Okay? And you just plug it in like normal. So we've been talking about when something isn't a function, and frankly, it's really difficult to represent things that aren't functions as algebraic expressions, especially polynomials and rationals. Polynomials and rationals are pretty much always functions. Okay. Before we go on, I want to add that these, even what we know so far is kind of the tip of the iceberg for functions. We can build functions, more complicated functions, out of these functions. I know, functions all the way down. So this is a type of function called a piecewise function. Piecewise functions look like this. 2x plus 1 when x is less than 2, 3x when x is between 2 and 4, x squared minus 1 when x is between 4 and 7, and x minus 4 when x is bigger than 8. Oh, sure. Let's put an equal sign there. All right. So Sometimes these are called conditional expressions. Essentially, we've got a list of conditions. For any x I want to choose, this value of x satisfies one of the conditions. And which condition it satisfies determines which expression I'm going to use to evaluate the function. So for example, when x is equal to 1, that satisfies this condition. It's less than 2. It doesn't satisfy any of the others. So I'm going to represent this as 2 times 1 plus 1, so that's equal to 3. What about f is equal to 5? When x is equal to 5, which of these conditions does it satisfy? Well, it doesn't satisfy this one because 5 is bigger than 2. It doesn't satisfy this one because 5 is bigger than 4. It satisfies this one. So I'm going to use this expression to calculate the value of f. So it goes 5 squared minus 1. So 25 minus 1 is equal to 4. F of 9. So usually conditional functions are ordered according to where they sit on the line. In other words, there's an order to them so that it's easy to read through them. So 9 doesn't satisfy that, doesn't satisfy that, doesn't satisfy that. It satisfies that one. 9 is bigger than 8. So you plug in 9 minus 4 is equal to 5. And that's your output, and that's how you calculate your output. Interestingly, though, in a conditional expression, it's never possible for the thing to satisfy 2 of the expressions. Why not? Answer me this. What would happen if we had, say, what if it was like, what if the expression looked like that? So when f is equal to 5, this would satisfy 2 of the expressions. Would that be bad? Yeah. Is the answer 3 times 5, or is it 5 squared minus 1? Is the answer 15, or is it 24? So that violates the ambiguity kind of clause. It's against the rules for these intervals to overlap. Okay, let me change it back to the way it was. That was less than or equal to 4. An interesting thing, though, is the borderlines. Okay, so what about f is equal to 4? That looks like it's on the border between these, and that's really where these lines come in, whether or not it's equal. So you say, look, x is equal to 4, that's this one. This one won't let x equal to 4. So I'm going to use this equation to calculate it. 3 times 4 is equal to 12. Okay, and now the last part, what you've been wondering. What about x is equal to 2? What about f at x is equal to 7.5? Well, the 7.5, this one, when x is equal to 7.5, it falls between these two. And so there isn't a condition on here that satisfies. This particular value of x doesn't satisfy any of these conditions. That means the output's going to be does not exist. You like that? That's the empty set symbol. It means there's no answer. Similarly, when x is equal to 2, it's a lot subtler in this case because there's no, but this one doesn't include 2, x is equal to 2 in the interval, and this one doesn't include x is equal to 2 in the interval. So this one also does not exist. It's okay for the output to not exist. What's bad is if the output, if there's more than one answer. So there isn't here, and that's how to use a piecewise function. And let's get to talking about domains. Domain and range. Generally speaking, the domain of a function like that is any input. So I can put any value of x into that expression and get out an output. So x, all real numbers, like we said before. Okay? The range of this expression, though, you know what? I gotta tell you, sometimes it's all real numbers, sometimes it isn't. It's a real mess. We're gonna talk about this at a later date. So one of the big problems with writing functions out as polynomials is that it's really difficult to tell what the range is. And sometimes the range is really helpful to know. That said, all these things I said about all real numbers, we've seen some functions that don't have very good domains, like this, x plus 2 over x minus 1. Okay, so you can plug most numbers into this. 3, and you get 3 plus 2 over 3 minus 1, so that's 5 over 2, and it's a nice wholesome number. It's not a whole number, but it is wholesome. Nobody's mad at it. If you plug in x is equal to 1, you get 1 plus 2 divided by 1 minus 1, so that's 3 divided by 0. I wrote O. 3 divided by 0. 3 divided by 0 is an undefined number. You can take out your calculator and try it. 3 divided by 0. Ooh, it says error 2. The number of ways a person can explain why dividing by 0 doesn't give you an answer is, there's a jabillion ways to do it. We'll be doing it graphically in a few classes, in a few lessons. But until then, just know the domain of a rational does not include any roots of its denominator. Which is part of the reason we like talking about roots. So for example, 3x plus 2 over x minus 7, x minus 13, okay? So x is equal to 7 and x is equal to 13 are roots of the denominator. Okay? And that means that if I plug them into this rational expression, the function wouldn't exist. So if I plug them into my rational expression, I would get a number that does not exist. Okay? So, domain. We saw at the start that if the thing's output doesn't exist for a particular input, then that number is not part of the domain. So the domain is all x, let me rewrite this. X is all real numbers except for x is equal to 7 and x is equal to 13. That's how you say that. As for the range, don't worry about that for right now. We'll talk about it later. It's fairly complicated. Okay, so before we did a list of what's good and bad about different types of displaying functions in different ways. So a table and an arrow diagram. Let's do the same for a graph and for an algebraic expression. Good, bad. Good, bad. Good and bad aren't the right words. I think I mean to say advantages and disadvantages, but those are big words, and I don't want to spend all day here. So, all right. So what's good about a graph? It's easy to interpret. You don't have to do any calculations or anything. You just take a ruler and look up the answer. Algebraic expressions, they aren't easy to calculate. You have to do calculus. I mean, you have to do calculations. So it must calculate. So that's a boo. Another good thing about a graph is that it's straightforward to see. Straightforward. Domain and range. With algebraic expressions, the domain and range are tricky. Okay. Well, what's bad about a graph? Graphs are tricky to accuracy. Graphs are inaccurate in a way that equations or tables aren't. So with a graph, it's hard to be super accurate because you're still kind of eyeballing the values of the numbers. You might be off by a little bit depending on how accurate the graph is, right? So it's not very good for accuracy. Algebraic expressions are great for accuracy. Algebraic expressions are also very small, right? I mean, you might for a table, you're missing out on numbers, right? I mean, it's possible for there to be some outputs that just can't make it into the table because the table would be too long. Tables are huge. Graphs, not that accurate. Algebraic expressions, you have to do some calculations, but they're very small. So they're easy to interpret. I mean, they're easy to write out and explain and hold. So yeah, that's essentially it. The problem with algebraic expressions is you have to do calculations, and it's hard to talk about the domain and range. Whereas with graphs, it's hard to be accurate, but you can interpret all these things. Okay, so one last thing I want to remind you of is you don't need to calculate. Hold on. I'm just reaffirm the domain and range. So for polynomials, the domain is all real numbers. Always. For rationals, the domain is all real numbers except for roots of denominator. As for the range of them, I haven't told you how to figure that out yet. You actually have to do some thinkering. Okay, so let's review. Let's draw some medicine wheels. All right, so first off, functions. There's different ways to talk about functions. Numeric, so we can describe a function numerically, and by that we mean write out a table of numbers or write out an arrow diagram. Functions are relationships between sets of numbers. You put one in, you get one out. You can also do it algebraically. You can do it visually. You can also do it verbally. Like there was a time when math was almost all verbal, and somebody would be like, well, take this number and divide by 2 and then add 3. That would still be a function. You'd start out with a number, the number of cows that Ishtar had, and then you would end up with the number of bales of hay they needed to buy. You can still do it verbally. We just don't do it. They tend to be kind of clumsy. But the long and the short of it is there are different ways that we can go about talking about our functions. There are drawbacks and advantages to all the different types. It's not uncommon in this world for functions to still be displayed numerically as tables. It's not uncommon for them to be displayed in terms of arrow diagrams. I've seen those. Mathematically, we usually do it graphically or algebraically, but they're all functions. Okay. Then, graph, equation, function, relation. We're going to see this a little bit more next one. But essentially, there's going to be a relationship between graphs and equations. Anything you can write the equation of, you can draw the graph for. So, not all functions are graphs. There are some things that are graphs that aren't functions. Some graphs, just like some tables, fail the function test. That said, almost all equations are functions. We're going to get to them. But essentially, in all these cases, what we're talking about is relationships between numbers. Not just any sets of relationships, right? I mean, we're talking about in the arrow diagrams how the arrows always had to go one way. You could justify some other kind of arrow diagram where the arrows made sense, but that wouldn't be a function. We're talking about a very specific type of relationship between the inputs and the output numbers. And there's also domain, range, function, input, and output. Just keep in mind the different aspects to a particular function. You can think about a function in terms of the inputs correspond to the outputs, so maybe draw an arrow diagram. Or you can think about it in terms of domains and ranges, algebraic expressions. Okay. Long story short, we have a lot of other things to talk about. But that's it for function basics.